Hello, I'm Aaron Lohr, and this is the Endocrine News Podcast. If you're like me, when you hear about a study that talks about extending lifespan, your ears perk up a little. So get those ears prepared, because today we're looking at a study presented at Endo 2023 entitled Disruption of GHR in Middle-Aged Mice Enhances Insulin Sensitivity and Extends Male Lifespan. Joining me to talk about it is one of the study authors, Dr. Silvana Duran-Ortiz, a postdoctoral research fellow at Ohio University. Thank you for being here today.
Hi, how are you? Thank you, Aaron, for inviting me, and thank you to the Endocrine Society for the opportunity to talk about my research, because it's very exciting for me, at least.
And we're super excited to have you on the podcast. We're both excited. That's wonderful. All right, so let's dig in. What do we already know about the relationship between growth hormone action and lifespan?
Well, that is a heavy question, but the short answer to it is that we know that decreased growth hormone action extends lifespan. Now, let me elaborate a little bit about that. So, growth hormone is an anterior pituitary hormone that is secreted throughout the body in the blood. It binds to the growth hormone receptor, so basically it will act in any tissue that has growth hormone receptor. And although it is mainly known because its role in longitudinal growth or height, a growth hormone has other metabolic effects. So I'm going to start with one, which is that growth hormone induces the expression of another hormone called insulin-like growth factor 1, or IGF-1 for short. So IGF-1 is mainly produced by the liver, so about 75% of the IGF-1 that we have in circulation is by the liver, but it's also produced by many other tissues. So that's why usually when we talk about growth hormone, we talk about the growth hormone IGF-1 axis, because growth hormone induces IGF-1, and also a lot of the metabolic effects of growth hormone are mediated by IGF-1. Now, growth hormone has other effects, so it increases lean mass, it decreases fat mass, is involved in fluid retention. But besides all these metabolic effects, growth hormone is involved in many mechanisms that are associated with aging, such as DNA damage response, senescence, fibrosis. So all of these mechanisms are associated with aging. Also, the diabetogenic effect, or the anti-insulin effect of growth hormone, makes it very important for healthy aging. So, as I said before, it's a heavy question because there is a lot of research that points out to the fact that decreased growth hormone IGF-1 axis extends lifespan. And I'm not going to go through all the research, but I do want to point out 3 pieces of evidence that show this relationship. So the first one will be patients. So patients with Laron syndrome. So patients with Laron syndrome have been studied for decades by Dr. Laron, who was the one that discovered this syndrome in Israel, and by Dr. Jaime Guevara in Ecuador. And these patients have mutations in the growth hormone receptor that makes them insensitive to growth hormone since before birth. Now, these patients, because of the actions of growth hormones, they are short in stature, they are also fatter, so they have an obese phenotype. But even though they have this phenotype, these patients seem to be very healthy in terms that they are resistant to cancer. And even though they are obese, at least the Equatorian cohort, they are resistant to diabetes as well. Not only that, but researchers have seen that they have improved markers of healthy aging, such as decreased mTOR. So that is the first piece of evidence that I want to talk about. The second piece of evidence is a mouse model for patients with Laron syndrome, the Laron mouse, or the growth hormone receptor knockout mice. So these mice were generated in the lab of Dr. John Kopchik in Ohio University, my advisor actually. And Dr. John Kopchik generated these mice, and these mice have also inactivating mutations in the growth hormone receptor. So they are also insensitive to growth hormone since before birth. And other researchers like Dr. Berryman and Dr. List have shown that these mice also have the same healthy phenotype as patients with Laron syndrome. So they have increased fat mass and decreased lean mass, but these mice are also resistant to cancer, resistant to diabetes. They have also decreased markers of senescence in adipose tissue. They have a reduced fibrosis also in adipose tissue. And not only that, and probably the most important piece of evidence, is that these mice are called or have the prize for the longest lived laboratory mouse. So these mice live almost 5 years of age, 1 week shy of 5 years of age. So they are long, very, very long lived. The third piece of evidence, and in support of this relationship between decreased growth hormone and IGF-1 and aging, is caloric restriction. So diets that have some form of caloric restriction, such as fasting mimicking diets. A lot of these diets have shown to decrease IGF-1 and insulin levels. So again, another piece of evidence. Not only that, but now some of these diets have shown to improve the outcomes in age-related diseases, such as cancer and neural diseases. So basically, there is a lot of evidence pointing out to the same thing, and I can mention other mouse lines like the Ames mice, very much studied by Dr. Barkey and Dr. Brownborg. In terms of decreased IGF-1 signaling, we have another human case, which is the centenarians, the Jewish centenarians that have decreased IGF-1 signaling. We have also other mouse lines, for example, the mouse line made by Dr. Barzilai and Dr. Hoffman, that they have decreased IGF-1 signaling using IGF-1 antibodies, also extension of lifespan in females, basically. So there's a mountain of evidence pointing to the same thing. Decreased growth hormone, IGF-1 access will extend lifespan and health span.
So there is a lot of evidence, as you shared with us. We know a lot. Can you tell us a little bit about what you wanted to learn from the study that you're presenting here at Endo?
So we already know that decreased growth hormone and IGF-1 access extends healthy lifespan. Now, we know that mainly because of models or mouse models and other models like fruit flies, worm, other models, but all of these animal models have germline decrease, or before birth, decrease in growth hormone IGF-1 signaling. So that is how we know it. Now, what we didn't know and what we wanted to find out is if we decrease growth hormone action later in life, will we have the same beneficial health and lifespan effects that we see when we decrease growth hormone action at the germline stage? So that was the main question that I wanted and we wanted to ask. From that question, there's other questions that derive, like how far in life can we go by decreasing growth hormone action and still getting these effects? Are we actually getting the effects? Are we getting side effects? Is it a sex-specific thing? So there's many other questions that derive from that one, but the main one is, can we get the same beneficial effects in terms of healthy lifespan that we see in the germline mice if we knock out or decrease growth hormone action at an adult age?
So before we dig into your study, can you tell us a little bit why it's significant to study that when? Like, why does the age part matter?
So yes, in many contexts, we almost always say timing is everything, and this is true for many other places, especially the aging population, which is all of us. So the importance of interventions in aging is about the when. When do we want to start those interventions? So that's why it is the when question, it is important. So aging is associated with many characteristics such as energy decline, neuromuscular decline, body composition changes, age-associated diseases such as cancer and diabetes. So because aging is associated with all of these changes, in many societies, such as the scientific community, aging is seen almost like a systemic disease that can be modulated by interventions. So the thing is, like, which are those interventions and when to give those interventions, right? That is the question. For example, in terms of interventions, there are many candidates, but there is a specific example that is like many of the aging researchers did a meeting some time back, like around 2015, and this meeting and the outcomes of this meeting is actually published. This meeting was in Italy, and they, after like days of meeting, these researchers were asked to vote about which interventions will be more possible to extend healthy lifespan. And it was very interesting to see that the majority of votes went towards decreasing growth hormone IGF-1 signaling. So that is something that is there in the aging community and in the aging research community. Now, the question is when? When is the best time to give this intervention? Because as I said before, growth hormone is needed for many metabolic effects. So germline is not a very plausible time to do that. It's not very translational. So that's why the when question is very, very important.
I think we're ready. Why don't you tell us about your study?
My study wanted to see if this decreased growth hormone action will extend healthy lifespan at an adult age or later in life. So to do that, or to answer this question, we generated 3 mouse lines that have decreased growth hormone action at different postnatal ages. Now, how did we do that? So we have a mouse model. This mouse model has an inducible Cree-lock system. What does that mean? It means that basically these mice are engineered to have normal growth hormone action throughout their bodies until we inject a drug called tamoxifen for 5 days. And this tamoxifen at a specific time point that we decide. So we decide the age. And then at this point, this tamoxifen will help us to ablate or knock out the growth hormone receptor in these mice. So these mice, as the growth hormone receptor knockout mice, or as the patients with Lerner syndrome, will not have a functional growth hormone receptor, so they will be insensitive to growth hormone. So basically, that is the mouse model that we use. Now, when did we inject the tamoxifen? So we have 3 mouse lines. The first mouse line, we injected tamoxifen at 1.5 months of age, meaning that these mice have the growth hormone receptor ablated at 1.5 months. That will be like teenage years, okay. So puberty. The second mouse line, we have the growth hormone receptor ablated at 6 months of age. That will be about 30 to 35 years of age in humans, so adult age. And these 2 mouse lines are already published and out there. And the third mouse line, which is the one that I'm presenting here at Endo, is when we knock out the growth hormone receptor at 12 months of age. That is about 43 years of age in humans, so middle age. Now, we knock out the growth hormone receptor at these ages, and then we follow these mice to do metabolic characterization of these mice and to do longevity studies. And we have, like, besides the cohort of mice that we have in the longevity study, we have usually 2 cohorts of mice that we dissect at different time points in their lives to be able to study some of the cellular and molecular effects of knocking out the growth hormone receptor at different postnatal ages.
So after all of this, what did you find? And did anything in your findings surprise you?
Yes. Okay. A lot of the findings surprised me and excited me, actually. Oh, like, I'm going to start talking about the 1.5 months. So when we knock out the growth hormone receptor at a pubertal age, what we found is that we improved insulin sensitivity. That is something that we expected. And something that it was very surprising is that it extended lifespan, maximal lifespan in females. Now, these mice, because they were in puberty, they were still smaller than control mice. So the longitudinal growth was still stopped, to say it like that. Now, when we knock out the growth hormone receptor at 6 months of age, what did we find? We find that the longitudinal growth actually was not that stunned. The mouse were pretty much had the similar longitudinal growth to control mice. So that was a positive result. We also saw an improved insulin sensitivity in these mice, in male mice, and we also saw a decreased cancer incidence in these mice, which was very interesting. Also, besides the phenotype, the obese phenotype of these mice that we expected because we decreased growth hormone action, these mice didn't have any inflammation. So the inflammatory states or the inflammatory cytokines that we tested were not changed. They also had improved markers of aging. So, for example, lipid and protein oxidation was also decreased. And very important, we also saw an improved longevity in the females of these mice. So everything was right in the track that we wanted. Now, for the mice that I'm presenting right now, which is knocking out the growth hormone receptor at 12 months of age or at middle age, what did we find? And the most surprising part for me is that actually when I submitted the abstract to Endo, I was doing the longevity studies. Now we finished the longevity studies. And what we saw was a lifespan extension of both male and female mice. So both of the mice have lifespan extension. They are more, the males are more insulin sensitive as well. And we don't see in any decline or any detrimental effect of knocking out the growth hormone receptor in terms of neuromuscular activity. When we tested rota-rot test or grip strength, or when we did frailty testing, none of those were decreased, even though, as we expect, the body composition of these mice changed. So right now, with the results that we're seeing from the series of knockouts, of adult onset knockouts, what we can say is that even if we take out growth hormone action at a middle age, we are seeing a healthy lifespan extension with reductions of cancer, with reductions of lipid and protein oxidation, with improved insulin sensitivity, and extended lifespan in both male and female mice.
That's pretty exciting. I mean, there's a fascinating story developing here thus far in mice specifically, but what might your research or future research in this area mean for humans?
The bench to bedside transition is a very long road.
Oh, yes.
And a very difficult road, but it's a very exciting road. I think that the main thing and what excites me the most about this type of research, and this is not the only intervention that is being studied out there to extend healthy lifespan, is that there is, I have been seeing like a shift in the paradigm in terms of aging. So now aging is being seen as a metabolic disease, something that we can manipulate, and that the manipulation of aging can improve the quality of life of people, can decrease the incidence of many of the age-related diseases, which is almost everything, cardiovascular diseases, if we're talking about Alzheimer's disease, if we're talking about diabetes, if we're talking about cancer, almost all of these diseases are age-associated diseases. And we are seeing that if we intervene in somehow, either with a caloric restriction, with exercise, or with an intervention such as the growth hormone, IGF-1 axis, or any other intervention, we could improve the outcomes of all of the diseases. We can delay them, and we can improve the quality of life. And that is a paradigm shift that makes me very happy, to be completely honest. So the question here will be, which interventions are we going to use? And when are we going to use them? And how is going to be the formulation to use these interventions? We're talking specifically about the growth hormone action or decreasing growth hormone action. So in terms of growth hormone action, there is an intervention that is approved already by the FDA. That is the growth hormone receptor antagonist created by Dr. Kopchik. And this growth hormone receptor antagonist is safe. Is right now used for patients with acromegaly. And the thing with the interventions is, how is the formulation? So right now for the growth hormone receptor antagonist, the formulation is a daily injection, which is not the best formulation when we're talking about an intervention for aging. But there is a lot of research out there by many companies and by many independent researchers that are trying to make new formulations about growth hormone antagonists. They're trying to make oral formulations. and they are trying to make it long-acting. So there's other researchers working on the formulations to make it more available and easier for people to take. That is one thing. So while other people is working on the formulations, at least from our end, we can say that we saw that in a preclinical model, decreasing growth hormone action is a plausible possibility to extend healthy lifespan.
What more do you hope to learn through future research on this issue?
Well, I think that I was talking about the questions a little bit before. So, and that is the beauty of science. The beauty of science is that one question leads to another one and another one and another one. So I think that one of the main questions that I want to answer is why? Why are we seeing the effects, the metabolic effects that we are seeing in these mice? What are the mechanisms involved in the metabolic effects of these mice? So that is one of the questions that I'm very interested in answering. The other question is, what tissues are the most important? What tissues are the ones that are, all of them are important, but what tissues are the ones that are mediating those mechanisms? Another question will be, which other intervention can synergize or antagonize this specific intervention of decreasing growth hormone action and aging? So there are many questions to be answered, and I think that all of these questions are valid, and not only valid, but are necessary to be able to pave the road to interventions to extend healthy lifespan.
Well, this has been great. We are out of time. Dr. Durant-Ortiz, thank you so much for joining me today.
Thank you so much.
That's all for this episode. I hope you enjoyed it. If you did, you may also enjoy the Endocrine Society's new scientific statement entitled Hormones and Aging. We'll link to it in today's episode description. I wanted to say thank you to everyone who's been sending me emails about what you'd like to hear on the podcast. You're helping us plan future episodes, and we have a good list going. If you'd like to add to it, you can email me at podcast@endocrine.org. Until next time, thanks for listening.
Endocrine News podcasts are a free service of the Endocrine Society. To learn more or to become a member, visit the Society's website at www.endocrine.org.